Chapter 32 is about geometric optics or ray optics. Anytime you see something, the only reason that you can see it is because a ray of light coming from that object literally enters your eyeballs. So, in order to see something, you know if you see it that light is reflecting off that object and coming to you. Now, there's a couple of ways light can actually come from an object. There are a few things that are luminous and actually emit light. Those are things like the sun, lightning bug, a flame, any type of fire, a light bulb filament, things that actually generate and give off light. Most things that we are able to see are what we call illuminated, which means that they reflect light. That includes the moon. The moon doesn't give off light, it reflects the sun's light. That includes this chalkboard eraser. You can see it because it reflects light. Paper in my hand. Anything you can see that doesn't give off light, light is reflecting off of it. When we do geometric objects, we start with the assumption that light travels in straight lines, and we call those straight lines rays. Okay? So this chapter is dedicated to geometric optics or ray optics. Section 32-2 deals with the reflection and plane mirrors. Plane is in the word flat. The first thing we want to do is learn that what the law of reflection is and how we measure angles in optics. Assuming this is a straight line here, that might represent a pane of glass, it might represent water, it may represent a lot of things. But when we measure angles, we measure them from a segment that is perpendicular or normal to that surface. So we call that a normal segment. If I have an incoming ray that's coming in like this, it hits the glass, part of it will be reflected and bounce off. This angle from here to here would be considered the incident angle. This angle from here to here would be the reflected angle, which brings us to the law of reflection. The law of reflection says the angle of incidence equals the angle of reflection. So if we have a ray of light that's incident at 37 degrees, it's going to reflect at 37 degrees. Okay. Now, when that light is reflected, there's really two types of reflection that can happen. The most common is something called diffuse reflection. In diffuse reflection, we generally have something that has a rough surface, and it might not seem rough. I mean, it might be something just like this piece of paper even. It feels pretty smooth, but if we could look at it microscopically, so when I say rough surface, I really mean microscopically, we would see that it is rough. So what happens is, if we were to zoom in on a surface, instead of being flat like we think it is, we realize that it's got lots of surface irregularities. And the result is, even if we send in a bunch of light that's nice and parallel, some nice straight parallel rays, what we find is they go bouncing off at all kinds of angles. And the result of this is that we cannot get image formation. That's why when you look at yourself with a piece of paper, you don't see yourself with a piece of paper. You don't see yourself on the back of that. Most of the things when we pick up, we don't get image formation. However, certain things do. And when that happens, we have something that we call specular reflection. We have specular reflection. Things are very smooth, even at a microscopic level. Those things include glass, mirrors, polished metal, and even water. If the surface of the water is nice and still, all of those things are smooth at a microscopic level. So now if we have a beam of parallel light rays come in, they will all reflect following the law of reflection. I'm not drawing this perfectly, but in a very predictable manner. And we do get image formation. Okay. So we're going to look first at the simplest of mirrors, and that's a plane mirror. That's a flat mirror like what you have on your bathroom wall at home. We want to look at how images can form using plane mirrors, because it is fascinating. When you look at yourself in a mirror, the light that you see that enters your eye appears to come from behind the mirror. It appears as if somebody is actually, if you're standing 2 feet in front of the mirror, as if there's actually light coming from 2 feet behind the mirror. So there's a mirror. We're going to draw just a line perpendicular to it, just so that we have a kind of a reference frame here. Okay. Most of the time when we draw an object, what we will use is an arrow. And the reason we use the arrows, for one thing, is it's directional, because sometimes when we form images, we find that they're right side up, and sometimes when we form images, we see that they're upside down. So an arrow is a good thing for indicating whether or not it stayed right side up or whether or not it became inverted. So let's put our object, I'm just going to put it right about here. It doesn't really matter how big it is. But there it is, out in front of the mirror. Now, if we have a plane mirror, we know that the angle of reflection will equal the angle of incidence. If we have a ray that comes in that is perfectly parallel or perfectly perpendicular to the surface that's parallel to that line there, we know that it'll go in, hit the mirror, and bounce right back out. But if we think about it, if it comes out to your eye, that is the same as if it might be coming from back here. If you're over here someplace looking, here's your eye. And when it hits here, all your brain knows is that ray is coming from this direction. It doesn't really necessarily know where that ray originates. Okay. Now let's look at another ray. Let's think for a moment. Suppose I have a ray of light, different color, I'll this one in green. It also enters the mirror, crosses right across the tip of that arrow. So it's going in like this. It hits that mirror, and it's going to reflect where the angle of incidence is equal to the angle of reflection, and go off like this. Now again, your brain can tell which way it's coming, but it can't tell where it originated. So as far as your brain's concerned, it could just as likely have originated from back here somewhere. Notice these 2 points are both right here. So if we could draw lots and lots of rays, and it could get really complicated. But in the end, what we see is, as far as your brain can tell, this light coming off the tip of the arrow over here could be coming off the tip of the arrow back here. This distance from here to here is called the object distance. This image from here to here is called the image distance. If we're working with a plane mirror, a flat mirror, the object distance and the image distance will always be exactly the same. Another thing we'll notice is it will appear to be the same height. We don't get any magnification with a plane mirror. And it's an upright image. Now, is there any actual light back behind the mirror? And the answer is no. Probably there's some sheetrock or something back behind the mirror. Okay. All of the light actually stays on this side. Since there's no actual light back here, we call that a virtual image. So plane mirrors form virtual images. They are upright. Anytime you get an upright image, it is in fact a virtual image. Okay. So plane mirrors form upright virtual images with no magnification. If you have a real image, that's the other possibility. You can put a piece of paper where that real image is formed and actually see it, like a movie screen, where they projected image. In the old-fashioned ones, you could see the light coming down behind you where they projected the image on the screen. That was a real image. The light is actually there. This is not a real image because there's no light rays back here. That makes it a virtual image. Okay. And that concludes this first lesson about reflection and plane mirrors. Pretty straightforward. The angle of incidence is equal to the angle of reflection, and plane mirrors produce virtual, upright images with no magnification.